In this video, we're going to be doing operations with radical expressions. And the thing to think of radical expressions as basically same way you would think about adding like terms. So what we're going to do first is we are going to obviously look at something as simple as x plus x. Well, when we add that together, we're not changing the exponents or anything. It's simply one expression added to another. So it's going to be 2x, right? X plus x is 2x because we have two of them. Well, if I have the square root of 2 plus the square root of 2, then I have 2 square roots of 2. And the whole thing is this has to be, as always, the same base and the same degree, or in this case, the same root. Because again, roots are fractional exponents, or same fractional degrees. So if this was x squared plus x, I couldn't add them together any more than if this was the cubed root of 2 plus the square root of 2. I couldn't add them together. So in all of these cases, they have to be the same base and the same root or the same degree. So in the first one, it's really easy. I have 3 square roots of 3. I have 2 square roots of 3. So altogether, I have 5 square roots of 3. I have a negative 2 square root of 2. I have a negative 7 square root of 2. So I have a negative 9 square root of 2. Same thing here. We have 5 of the square root of x's. I have not negative 9 square root of x's. So I have a negative 4 square root of x's. And the same thing works for every single one of these, where we're not combining the bases, we're not combining the exponents, we're simply combining the coefficients in front of it. So all of these work very much the same. So I have negative 4x and a negative 3x together. That's a negative 7x of these square root of 2y's. Now when I'm looking at this one, these cannot be added together because they do not have the same base. They have the same degree. They're both square roots, but they do not have the same base. But we can do ourselves a favor and we can simplify the radical. So go ahead and do that. So doing a little work here, remember the 4 on the outside of each radical just has to come down and become part of your expression. But then I simplified the radical 72 and the radical 50 until I got them to be 24 square root of 2 and negative 20 square root of 2. Now they have the same base and they have the same radical, or the same exponent. So 24 minus 20 is 4 with the square roots of 2. So go ahead and simplify 7 and 8. Simplify the radical and see if we can't combine. Actually, go ahead and do 7, 8, and 9. So here's a lot more other work. Again, basically, we can combine them once we've simplified. And of course, sometimes we can't simplify them and we have to leave them as they are. But in each of these problems, they can be simplified down to more concise simplified radicals. And if you'll notice at the beginning of number 10, I started to break it down into I can take the square root of 4, but I can't take the square root of 5 and the square root of x. Well, if two items can't be taken the square root of, you can put them both together under the radical. So I don't have to write radical 5, radical x. I can write radical 5x. We can pull and put these together as long as everything is multiplied and divided. Again, like I said in a previous video, you cannot take the square roots or pull apart things that are added or subtracted. So if you notice, each one of these terms is taken care of on its own. And we're not combining anything under the radical in between this, just only within itself. So in multiplication and division of radicals, we can combine things underneath the radical. Sometimes it makes things a little bit easier for us. For example, square root of 3 times the square root of 27 is going to be the square root of 81, which I can definitely simplify. Now these I would honestly, if you have two things multiplied, I would put them together and see if it doesn't make our life easier. So we can combine things under the radical because they have the same root. If they're different roots, it's a little bit more complicated, and that's another video. But x to the first and x cubed is x to the fourth. Y to the fifth and y to the first is y to the sixth. And then taking the square root is simply taking half of each exponent. Doing the same thing again, I've got 2 and 18, those combine to be 36, and this is still all under the radical. I'm just combining under the radical. I haven't taken the square root or anything like that. So this x and x to the fifth is x to the sixth, and then y cubed and y to the first is y to the fourth. And doing that, I can take the square root of the first one, I can take the square root. These are all beautiful, perfect squares that I can take the square root of. Now in this, we can distribute. I can go the square root of 6 times the square root of 6, which is the square root of 36. I can do the square root of 6 times the square root of 3, which is square root of 18. And of course, simplify any radical that you possibly can. Same thing down here. We can distribute. Square root of x times the square root of x is the square root of x squared. That's going to be simplified in a minute. Square root of x times the square root of y is the square root of xy. That can't be simplified, so I can simplify the first, but I cannot simplify the second. Now this one, like any other binomial, we can't just square one and square the other. We have to write out the binomial twice. And then we have to do the FOIL method. So 3 times this is going to be 9 and the square root of x squared, which we can simplify later. Then we go 3 square root of x times y. Well, the y is not under the radical, so that becomes part of that lead stuff out in front. And then I have the square root of x. Here, when I multiply the inside, this is going to be the 3 and the y. The y is not under the radical, so it becomes out in front, one of the coefficients. And then the square root of x comes here. And then our last is a negative y times negative y, which is a positive y squared. So there's a couple things that can happen. Number one, we can simplify that. The 9 is already on the outside, so I don't take the square root of it. But the square root of x squared is x. I've got 3 y's of my square root of x and 3 y's of my square root of x, so a total of 6 y's of my square root of x. And then I have y squared here. So go ahead and FOIL and try the other ones. And they should be the answers when you distribute the rest. When dividing rational expressions, again, you can pull them apart or put them together the same way you could with multiplication. Again, only multiplication or division. So if I have something like this, where I have the square root of 50 over the square root of 2, I can put them under the same radical here and say that's the same as square root of 50 over 2, which is the square root of 25. And we know that's 5. Same thing here. We can simplify this. We can put this entire expression under here. So I have the 24xy cubed, and I also have 6, and that I'm trying to extend that down here, 6xy. So again, still under the radical, 24 divided by 6 is 4. X over x becomes 1, and then I have y squared. So then I can take the square root of each one. Square root of 4 is 2. Square root of y squared is simply y. But what if I can't divide it out? And this is where we come to rationalizing the denominator, meaning that I need to have a rational number in the bottom. So, and anything other than a perfect square in the bottom or in the denominator is irrational. So the simple thing is we're going to create a perfect square on the bottom. So what I'm going to do is, if I have the square root of 6, well, I can multiply it by another square root of 6 down here. So now I have on my denominator, zoom in a little bit. So we have the square root of 6, and I'm going to multiply it by the square root of 6 on the bottom. So now what I have on the bottom is square root of 36, which of course is 6. So my bottom, or my denominator, is now a rational number. But of course now I've changed the value of it, and the rules of fractions going all the way back to elementary school is whatever we do to the denominator we have to do to the numerator. So I'm going to multiply top and bottom by the square root of 6. Well, 1 times the square root of 6 is the square root of 6, and so that's what becomes the numerator up here up top. And it doesn't matter what it is. So if I have here, I need to rationalize this denominator. Well, the square root of x, I know that if I multiply it by the square root of x on the bottom, then I will get the square root of x squared, which of course is now a lovely rational number of x, rational value, excuse me. So now I'm going to multiply the top times the square root of x, because whatever you do to the bottom or to the denominator, you have to do to the top to keep it an equivalent fraction. So 5 times the square root of x is 5 square root of x. And then this will become 5 square root of x. Now I want to stop here for a minute and talk to you about how many students I have who are tempted to cancel these denominators out. Because, oh, I have an x on top and an x on the bottom, but we can only cancel out or reduce it down to 1 if they have the same degree. This does not. This value up in the numerator has a square root on it, so it is not the same as just eliminating it with the x. You have x to the 1/2 or the square root of x, and you have x down here. So this is how it works if there is a mononomial, or one term, mononomial, there we go, in the denominator. But let's look at what happens if I try to do the same idea when I have more than just the radical in the denominator. So let's say I did this. I saw that square root of 3, and I just multiplied by a square root of 3. So on the bottom now, I have to distribute. Remember, it doesn't just multiply by that, it multiplies by both. So I have the square root of 9 when I distribute, that times that, and then I have 1 times the square root of 3, which is the square root of 3. So when I reduce that, or when I evaluate it, square root of 9 is 3, but I still have the square root of 3. And that doesn't help my situation out at all. This is actually still giving me a radical in the denominator. So when we have a binomial, what we're going to do is we're going to use what's called the conjugate. In simplest terms, it's the same binomial with opposite signs. So if I have square root of 3 minus 1, then my conjugate is going to be square root of 3 plus 1. Well, of course, whatever I do to the bottom, I have to do to the top. So let's finish that out. Well, what does that do? Well, let's at the top, obviously, that's just going to be the square root of 3 plus 1. But let's look at what happens. You might recognize that this is actually going to become look like the difference of two squares. But let's FOIL the entire thing out. So we got to multiply. So my first times my first is the square root of 9. Then my outside, square root of 3 times 1 is the square root of 3. On the inside, I have negative square root of 3. And then on the last, I have negative 1 times 1, which is a negative 1. Extend that all the way out. Excuse me. So then, still have the square root of 3 plus 1 in the numerator. And the middle terms, if we've done the difference of two square looking binomials, or if we've done the conjugate, the two terms in the middle always cancel out or become 0. So I have the square root of 9, which is 3, minus 1. So what I have now is square root of 3 plus 1 over 3 minus 1, which is 2. So let's do this again. I have two radicals. It doesn't matter whether I have one or whether I have two. But the thing is I have to multiply by the conjugate, which is same binomial, opposite signs. So let's do this. It's the same binomial, but opposite sign. And when I mean by opposite sign, I mean just in the in between. I'm not changing the sign of the square root of a and the square root of b. I'm simply talking about the sign that's in between them. So let's do some distribution here. So I got to multiply this out here. So square root of a times square root of a, square root of a squared. And this becomes the square root of ab. Well, on the bottom, if I'm doing my good old FOIL, I've got the square root of a squared. I've got the outside, which is a positive square root of ab. The inside, which is a negative square root of ab, which again is going to cancel out or become 0. And then I have the negative square root of b squared. So on the top, square root of a squared is a minus the square root of ab. All over, again, these become 0. So square root of a squared is a minus b. And once again, go back to algebra, resist the urge to reduce. Do not cancel out my a's and b's. These are parts of polynomials. The only way you could reduce within these fractions is that everything is multiplied or reducing factors.